Thank you very much, Kyle, for the invitation. So I'm really honored to give a lecture here in this range of really excellent speakers. And I hope I can live up to this challenge. So my talk today will be about calculating macroscopic response from diffraction and especially coexisting phases. So I have the benefit I can build up on what Jacob showed you 2 weeks ago. He gave a really excellent talk, and so I will complement a little bit on this topic, and I will show you how we can describe the macroscopic properties of materials as a function of the atomic structure. Yes, so that's the basic motivation. We would like to bridge fundamental science and application. So we use photons or neutrons or electrons to investigate the materials, and we try to describe the structure properties relationships. So this means we go all the way from a macroscopic sample, so we have samples in the range of centimeters or millimeters down to the atomic scale. And this means we have to bridge 8 orders of magnitude in order to describe the macroscopic properties and response. So how do we do it? So we use photons, normally at synchrotrons, like Jacob described very deep, in a lot of detail last time in his talk. Here the advantage is that you have high angular resolution and you can do fast measurements, even time-resolved studies. Neutrons are also a good tool for characterizing the electroceramics. Here you can also see magnetic ordering, and especially the oxygen contribution here is quite high due to the high scattering length of oxygen with neutrons. And also microscopy is important because here you can have a look at the microstructure, domain structure, just the local structure of the materials in order to correlate this with the average information you get from diffraction. So I guess as a typical synchrotron experiment is sketched like here. So we frequently go to the PCO2 instrument at Petra 3 in Hamburg at DESY. I also helped building up this with this beamline here, and so typical experiment looks like this. We have our ceramic samples here with electrodes. We apply an electric field, and then we use a 2D detector, typically in this setup. So we put a direct beam at one corner, so that we have at the most extreme is a vertical cake which we use, and then a horizontal cake, and you have all the different orientations in between, and like this you get good texture information. So this means you can do this all your orientations within one shot. So this means your time resolution is basically the highest frame rate you can get with the texture with the detector, and typical sample dimensions are 1 by 1 millimeter. So the beam is typically also 1 millimeter wide. For neutrons, it's a bit different. Usually you need larger samples. So here I depicted the example in Munich at a research reactor. So this is everything is like 1 order of magnitude bigger. So you have a really large detector that would probably the whole instrument would fit in a small room. And so we build a sample environment here. We can investigate about a cubic centimeter, so even full devices would be possible here. And we use metal contacts to apply the electric field. And for insulation, we use SF6. In other experiments, you can use fluorinate, which is a hydrogen-free electrically insulating liquid. Yeah, here this is the sample environment here in action. We have a sample stage where you can orient the sample in different orientations with respect to the beam. Okay, so in Ferro talks, probably you would think, yeah, we don't really need the basics. And anyway, I will just briefly outline the classic model which stands behind the ferroelectricity. So we are normally talking about perovskite structures. So this means we are above the Curie temperature, we have a cubic structure outlined like this. And when you cool down below the Curie temperature, you have a polarization. So in this case, it's a tetragonal polarization along the 001 axis. And this is accompanied by a deformation of the unit cell and the formation of domains in order to compensate for the polarization and stresses in the grains. And when you apply an electric field, you have the inverse piezoelectric effect. So we also call it lattice strain. It's the intrinsic effect of the unit cell. And you have domain switching. So this means the domain switch along the applied electric field. And these two together, these effects, they result in an elongation of the ceramic sample, which can then be used for the application. And then you can measure these macroscopic strain loops shown like here. And the nice thing with X-ray or any powder diffraction is that you can see these effects directly in the diffraction balance. So Jacob showed that last time in his talk already. So here we have a tetragonal example. This means the 200 reflection shows a tetragonal splitting. And when we look then at the 111 reflection at a special orientation, we can see a shift as a function of electric field. And this is a direct observation of the intrinsic effect. And when we look at the 200 reflection, we see that the intensities change. And this is a direct observation of the extrinsic effect of domain switching. And this is well known now in the literature. Many people use this. So Jacob explained this, how you can fit the reflections and get detailed information about the material behavior from these changes in reflection intensities. And also so here, there's a nice example from David Hall, where he showed that when you have a tetragonal composition, like I showed you before, we have a tetragonal splitting and a shift of the 111 reflection. And in a rhombohedral symmetry, you have a rhombohedral splitting in the 111 reflection, and the 200 reflection is shifted. And from the fitting, you get can get some nice information, like here the sine square psi dependency, which is known from texture. Okay, so when we look at PZT, a typical material which is still technically used, here we see the phase diagram. We have here a morphotropic phase boundary. It's almost vertical and separates a rhombohedral stability region where you have the polarization direction along the 111 direction from a tetragonal stability region with a polarization direction along the 001. And in this region here around the phase boundary are actually the most interesting compositions, because here you have highest properties. But this also means, this also means that here you usually have phase coexistences. And sorry, I'm not sure why this happens. Sorry. Some time ago, we tried to minimize the texture effects by orienting the sample in a special orientation. So this means we went to 45-degree angle, and then you see that here in the red sample and the blue sample is an untextured sample in the capillary, and the red sample is the pole sample at 45-degree angle. You see that the intensities are almost the same. And so we try to quantify this. And the reason why this happens is because when you imagine, so you have an angular sensitivity with diffraction. So this means when you have your sample at 45 degrees, and so the diffracting domains have either the orientation like this, which is almost with the polarization direction almost parallel to the incident beam, or almost perpendicular to it. So this means at 45 degrees, when you apply the electric field, like shown here, there will be no domain switching. So you won't see the domain switching effect and might get structural information. So we did this experiment. We applied the electric field. Sorry, wrong direction. And what we saw is that an additional reflection appeared here in between the tetragonal reflections. And yeah, the reason is because when you have your electric field vector here in between the tetragonal directions, it's much better for the material to switch to the rhombohedral symmetry, and this can be considered as some sort of 54-degree domain switching. So it's a field-induced phase transformation from tetragonal to rhombohedral, and is fully reversible. And that's one reason why the PCT materials have such high properties around the morphotropic phase boundary. So when we look again at our individual reflections, we talked about these two orientations already with electric field. But when you go to special orientation, like the 45-degree angle, you can see the additional appearing reflections here, and you can see this third strain mechanism. So this means the classical model is incomplete. You also have to consider phase transformations when you are close to a phase boundary. So that's something you should always keep in mind. So, and that's why we thought, yeah, okay, why just look at individual reflections? Isn't there a possibility to use just the whole diffraction pattern, all information we collected? So in this case here, we have a schematic view of neutron diffraction experiment. So here you have also your ceramic sample with electrodes, and you orient it with different angles to the incident beam. And like this, you can collect the orientation series to investigate the texturing. And our approach was now to make a full pattern structure and texture refinement with a program package mod, and I will show you some details about this now. So here's again this typical PCT sample, and you see again here the diffraction pattern. So here is the 2 theta angle, and vertically you see the orientation angle. So this means this 2D information gives you the full orientation series. And on top are the measured patterns, and here is the calculated, so the Rietveld refinement. And here the 111 and 200 reflections are magnified here, and you can see that there's a really complex change in the intensities and also reflection positions, as I explained before. And when you apply an electric field, you have a strong change in response, in the structural response, and you see that the Rietveld refinement works really well, so we can explain the full pattern. And with this, we get really detailed information about the material response. So we get the domain switching for the coexisting phases. We get lattice strain for the individual phases, and we get information about the phase transformation. And this all within a single experiment. That's the nice thing. So we get all necessary information to explain the macroscopic behavior just with this diffraction experiment. So how does it work? So we call this the strain texture and Rietveld analysis for piezoceramics, abbreviated STRAP. And so basically we have 3 models. So we have the phase fractions we get from a classical Rietveld refinement, but on top of that we have a strain model where you can explain the shifts of reflections. And we have a texture model where we can, at the different orientation, we can see these changes in reflection intensity. And so here is now magnified this special 45-degree angle where you have the additional rhombohedral reflection. So this means within these 3 parts of the refinement, we can quantify all three strain mechanisms in the material. And like this, we get now really detailed information. For example, we can look at the tetragonal and the rhombohedral phases and at the individual strain mechanisms. So you can see here that in the tetragonal phase in this material, we have a rather low lattice strain, which goes to 0 at the cohesive field. We have a domain switching strain, which always has a remnant value. And for the rhombohedral phase, it's a bit the other way around. We have a higher lattice strain and a lower domain switching strain. And with the phase fractions together, we can now calculate the macroscopic strain loop. So this is shown here in blue. This is from the neutron diffraction experiment. So you see it's, and the red curve is the macroscopic measurement. You see that the agreement is okay. It's not exactly correct. So we have here deviations in the cohesive field and the maximum strain, but the explanation for this is the largely different frequency, because the neutron diffraction takes a long time. Every individual measurement takes a few minutes, and we have to do many measurements at different fields and orientations. So 16 microhertz means it's more or less a full day. And this is known as creep in exactly this material. So this means when you apply the field and wait, for example, 600 seconds, you have quite a strong drift. And Sophia Esslinger, a PhD student, so we could explain this by the different frequency, the cohesive field behavior. And Sophia Esslinger, a PhD student, so she built a sample environment where she could apply the electric field macroscopy and measure the strain macroscopically very slowly here in red. And then you can see that the agreement is really nice. So we have a perfect agreement between the diffraction, the strain calculated from diffraction, and the macroscopically measured strain. So that means we can explain the macroscopic behavior just with our atomic model, and we get really detailed information out of the experiment. So some time ago, we made a very simple assumption. With this 45-degree experiment, so we said our field-induced strain is basically just a change in the z-axis. And then when we normalize it with the electric field, we get something like a Piezo coefficient. And then we can weigh it with phase fractions here and get like the phase-weighted Piezo coefficient. And when we do this with these results here from the refinement I just showed you, and when we compare it, we see already here in this image that it looks quite similar. And when we superimpose it, it's a really remarkable agreement. So this means we can even we even recalculate the piezoelectric coefficient. And now the big difference here now is that we even get information on the individual phases. So because we all have all this information, when we look at the tetragonal phase, we see it's a rather normal D33 curve. So we have about the same maximum here around the cohesive field. But when we look at the rhombohedral phase, we see an extreme maxima here around the cohesive field of around 2000. So this means the rhombohedral phase seems to play a really big role in the high properties of the material. And phase-dependent D33 information is only possible with this type of investigation. Okay, and finally, when we look at the unit cell itself, so when you remember in the beginning, I described the inverse piezoelectric effect is actually. The idea is that you have an elongation of the unit cell with applied electric field, but when we look at it, we see actually the exact opposite. So this means with increasing field, we have a decrease in unit cell distortion. So one reason for this is because we always look at an average structure. So this means we have only one set of unit cell parameters, even though depending on orientation, they will be different. But this means, so with the higher the field is, the more domains will switch. And the resulting z-axis, because an a-axis will become a z-axis and the final z-axis will be lower than the original one. And that's why the average distortion of the tetragonal units will decrease with increasing field. For the rhombohedral phase, it's different. So there you can see a really big maximum around the coercive field, while for the rest of the hysteresis, the values stay more or less constant. And when we look at the permittivity, we see that the quite similar curves observed here. So this is the small signal permittivity and the large signal permittivity. So this means so we still don't really fully understand these results, but it looks a bit like that the reversible and irreversible processes come from different phases, as it looks like here from these results. Okay, so now can we apply this to lead-free piezo ceramics as well? So for this, for example, we had a look at the classic BNT-BT phase material system, solid solution. Here's the phase diagram. Around 6 or 7% here we have a phase boundary again. We also have a rhombohedral and a tetragonal phase on both sides of the phase boundary. And at the phase boundary itself, the structure is rather complex. There's still a lot of investigations going on, what exactly happens around here. So when we look at the structure at the phase boundary at around 6%, for example, when you apply an electric field, we see that we have here the relaxer state, and when we apply the field, we have an irreversible transition to the ferroelectric phase. And so we investigated this with high resolution X-ray diffraction, and we saw that even though the materials are indistinguishable in the unpoled state, with field you have a strongly different response. So in the BNT6PT you have a large rhombohedral splitting and a small tetragonal splitting, and it's the other way around, a small rhombohedral splitting and a large tetragonal splitting in 7PT. So just a small change in stoichiometry leads to a strong change in response. And when you heavily dope it with here in this case KNN, so about 2% KNN, so it makes the system quite complex now. From a chemical point of view, you get a really reversible behavior and a very large recoverable strain. However, we thought maybe it's better to go a little bit off this phase boundary to the more tetragonal compositions, like they are used as PZT as well. So you're also quite far away from the phase boundary. And so we changed our processing route a little bit. For BNT, we used sodium hydrogen carbonate instead of sodium carbonate. And when we sinter it in oxygen, in pure oxygen, we get a really perfect microstructure. And so this is the air sample. It looks like a normal ceramic sample, but the oxygen sample is actually translucent. So we really have no porosity. And finally, here at the air sample at the surface, we even see all existing phases in the phase diagram of BNT. So this means there might be an influence of the oxygen partial pressure. And we also changed the A-side stoichiometry. We adjusted it to the stoichiometry which gives you highest insulating properties. And with this, we synthesized the BNT12PT, so 12% barium titanate, and investigated it here with synchrotron radiation with different frequencies. And you can see when you apply the electric field at a 200 reflection, you see a strong tetragonal splitting. But there's already a frequency-dependent change in the response. So the magnitude of the phase transformation becomes smaller for higher frequencies. And in the remnant state, it always goes back to the pseudo-cubic state. So this means we have a fully reversible behavior, even though this should be a ferroelectric tetragonal ferroelectric, this material. So this means the processing already made a big impact on the electric field induced response. And here you can see it again. We investigated this, as I said, with different frequencies, here with the 2D detector, and then we used stroboscopic techniques to get the different frequencies. And so the interesting thing here was that we could see a gradual shift of the reflections, and we could explain this by self-heating at higher frequencies. So this means the change in field-induced phase transformation is actually a temperature effect, because at 100 Hertz you heat up the sample so much that it's almost at the cubic state already. Anyway, when we do the refinement of the different frequencies, also especially the low frequencies, we can see that the behavior compared to PZT is fundamentally different. Again, we have two different phases, but in this case, the tetragonal phase only shows domain switching strain, and the rhombohedral phase only shows rhombohedral lattice strain. So this means it's not another combination in both phases of both strain mechanisms anymore. It's a clear separation. And with the phase fractions, we can again calculate the macroscopic strain loops. And when you compare to the macroscopic measurements, you see that the agreement, at least for the low frequencies, is quite good. So this means this rather simple curve here, there's a really complex structure underneath in the structural response. And the behavior is fundamentally different from PZT. So this means this is one reason why it's still so difficult to find lead-free alternative materials, because the behavior is just completely different compared to PZT. Okay, as a final example, I would like to show you a little bit about bismuth sodium titanate with strontium titanate. So there is some sort of phase boundary at around 25% strontium titanate. So you get also pseudocubic structure. The reflection width decreases from this point on. And so we did again neutron diffraction, and we could do the same refinement. We could explain the structural response to the field. And it turns out that this is also has a very fully reversible behavior. So this means in the remnant state, it looks pseudocubic, and when you apply the electric field, you get splitting, rhombohedral splitting, tetragonal splitting, and even superlattice reflections. So our idea is that depending on how the grains are oriented, you get either a ferroelectric tetragonal material or an antiferrodistortive rhombohedral structure. And so Matthias Acosta, he made even in situ TEM measurements, and with image subtraction, he could estimate the elongation of the grains, and he found out that in TEM, the samples are elongating more than 2%. So this means this reversible field-induced symmetry change leads to an enormous strain in individual grains. And last time, Jacob, he showed a nice paper from 2005 where he theoretically determined the maximum texturing in these in different symmetries. So it's 2 for the rhombic structure, 3 for tetragonal, and 4 for rhombohedral. And so that was initially a problem for us, because so we did a refinement here of this BNTST, and the result was, so for the tetragonal phase, we have a maximum texturing here of 4, and for the rhombohedral, we have a maximum of 6. So here in gray, you see Jacob's maximum texturing, and it's clearly above that. So how is it possible? How can we have higher MRDs than the theoretical maximum? So once we met, Jacob and I, when we met in Australia, I asked him about this problem, and he modified his script. And we could then calculate what theoretically happens. So this means we just said, okay, whenever the polarization direction is more towards a rhombohedral direction, then let the structure be rhombohedral, and when it's close to a tetragonal direction, let it be tetragonal. So this is green for rhombohedral, red for tetragonal. And it turns out that we get a theoretical phase fraction then of 40% tetragonal. In our case here, BNTST, it's 47%. And so Jacob mentioned that last time, that the maximum polarization you can achieve is about 38% for tetragonal and 68% for rhombohedral, and monoclinic it's 95%. And when we look at these phase coexistences, we get results of we get more than 90% polarization. So this means there's a significantly higher degree of domain alignment when you have a phase coexistence. And so we can calculate the maximum theoretical MRD for phase coexistence, and then actually we end up with more than 7 for tetragonal and for rhombohedral, and rhombohedral is about 7. And then our refined values lie well within these boundaries, and we can say that there's no contradiction to the theory. But this is so this means with phase coexistence you have different results than when you look at single phase materials. Okay, so this leads me to the conclusion. I hope I could show you that all strain mechanisms are accessible in one experiment. When you do when you measure different sample orientations, the strap algorithm reveals unprecedented details in strain mechanisms, and we can also apply it on lead-free materials. But then we see that lead-free and PZT are fundamentally different from each other. And with the different techniques, photons, electrons, and neutrons, it's possible to reveal a complex correlation between the structure, microstructure, and properties. In the end, I would like to acknowledge my team, my PhD students, my former postdoc, and of course all students who helped contributing to my group. And of course, the funding agencies and all of my colleagues, and of course everyone else who is not on the list, which I forgot. There wasn't maybe not enough place here. And you for your attention. Thank you.